For years, Boeing has studied an aircraft that refuses to fit into any existing category. It's too large to behave like a narrow body, yet too efficient to resemble a traditional wide body. Informally called the Boeing 797, it remains unlaunched but far from forgotten. For decades, airline networks were built around the simple assumption that demand and aircraft would grow together. But that logic has begun to fracture. Many long-haul routes no longer justify the capacity of wide bodies, while narrow bodies stretched to their limits are increasingly being asked to fly missions they were never originally designed for. The retirement of the Boeing 757 widened this gap and removed an aircraft that was capable of carrying passengers across oceans without the weight of larger jets. At the same time, airlines have shifted toward point-to-point connectivity rather than relying solely on massive hub flow. This has created demand for aircraft that can profitably link secondary cities across continents. Manufacturers have responded by extending narrow-body range, yet these aircraft still face payload constraints and passenger comfort trade-offs on longer sectors compared to wide bodies. What the industry lacks is an airplane engineered specifically for this middle space, not adapted into it. And that unresolved space is precisely where the 797 begins to make sense. In 2015, Boeing was ready to launch a new design. By 2017, multiple airlines had expressed interest. Boeing expected this new midsize airplane to generate 30% more revenue than narrow bodies and have 40% lower trip costs than wide bodies it'd replace. Looking ahead, which path makes more sense to you? More specialized aircraft or increasingly capable single-aisle jets? Let us know your choice in the comments below and we'll discuss both at the end of the video. In 2020, the plan was paused, then revived in 2021. By 2022, Boeing announced the program would be delayed again until new engines and development tools were ready. However, if the program moves forward, the Boeing 797 would almost certainly be designed mostly inside a digital engineering environment long before any physical structure is produced. This reflects a broader industry shift toward model-based development, in which an aircraft is validated virtually before manufacturing risk is introduced. Engineers can now simulate structural loads, fatigue behavior, thermal expansion, aerodynamic forces, and even maintenance accessibility with a level of precision that wasn't possible in earlier generations of aircraft design. The motivation behind this approach is as economic as it is technical. Errors identified during digital modeling can often be corrected with minimal disruption, whereas problems discovered after tooling is built have historically cascaded into delays measured not in months, but in years. Commercial aircraft have relied on circular fuselages for decades because the geometry distributes pressurization forces evenly. This minimizes stress concentrations and simplifies structural reinforcement. However, Boeing has publicly discussed studying a twin-aisle fuselage with a slightly elliptical cross-section for the new midsize airplane. This is intended to provide wide-body style boarding efficiency while avoiding the structural weight penalties typically associated with larger cabin diameters. Once a pressure vessel deviates from a circular shape, load paths become more complex, and localized stresses must be carefully managed through material orientation. This is precisely where a carbon composite fuselage offers advantages that traditional aluminum cannot easily replicate, since carbon fibers can be aligned along anticipated stress directions. This allows engineers to tailor stiffness and strength exactly where they are required. Large composite sections also reduce the number of mechanical fasteners compared to metal construction, to reduce fatigue exposure and long-term inspection demands. Yet, composites rely heavily on advanced inspection techniques because certain forms of impact damage are not always visible on the surface. But it's the wing that ultimately determines whether the airplane achieves the efficiency required to justify its existence. Any aircraft attempting to occupy the space between narrow-body and wide-body categories must be designed to deliver aerodynamic efficiency while remaining compatible with airport infrastructure designed around smaller aircraft. Industry analysis widely anticipates a high aspect ratio composite wing. This reflects aerodynamic principles already demonstrated on newer generation aircraft, such as the 787, where longer spans reduce induced drag and improve fuel efficiency. Yet span cannot grow indefinitely because gate compatibility imposes hard operational limits. This is why folding wingtip concepts have appeared in multiple industry discussions. Composite wings are intentionally designed to flex under load, sometimes by several meters during flight. This way, aerodynamic forces distribute more evenly and reduce stress concentrations at the wing root. At the center of this structure sits the wing box, which is the primary load-bearing element responsible for carrying bending forces to reach extraordinary magnitudes during turbulence. Fuel would be stored directly inside the sealed structure, meaning manufacturing precision is not merely desirable but essential. Although no official programming has begun and Boeing has not selected an engine, manufacturers have spent years studying the thrust class required to make such an aircraft viable. Most industry estimates place the requirement somewhere between 45,000 and 55,000 pounds of thrust. It is envisioned to use next-generation high-bypass engines, likely smaller than 787 engines, to achieve better fuel efficiency than current jets. Boeing has explored options with GE Aerospace, Pratt & Whitney, and Rolls-Royce. The engine is expected to power a middle-of-the-market aircraft, focusing on routes between 4,000 and 5,000 nautical miles. The 797 could even incorporate advanced and highly efficient or even hybrid electric propulsion systems if developed in the 2030s. The production strategy for any future Boeing clean-sheet aircraft may reflect the lessons learned from the 787. The globally distributed supply chain there introduced coordination challenges that took years to stabilize. Industry reporting indicates a stronger preference toward tighter supplier oversight and a more integrated manufacturing architecture, even if major structural components continue to be built across multiple regions. Automation is expected to play an expanded role, with robotic drilling improving precision and digital measurement systems verifying tolerances in real time. Augmented reality guidance tools are already being evaluated to assist technicians during complex installations. They could project instructions directly onto the structure rather than relying solely on traditional documentation. The objective now is production predictability, because airlines are purchasing delivery certainty as much as they are purchasing aircraft capability. However, building the airplane is only part of the challenge. Designing it to survive decades of cyclic stress may be even more critical. Every commercial aircraft operates within cycles of pressurization and depressurization, slightly flexing the fuselage during climb and relaxing again during descent thousands of times across its service life. Metal airframes eventually accumulate fatigue under these conditions, but composite structures behave differently. They resist crack propagation but require more sophisticated inspection techniques. Newer aerospace designs incorporate structural health monitoring systems like fiber optic sensors, capable of detecting strain variations in real time. This helps teams to identify emerging stress concentrations long before they manifest as visible damage. Aircraft are no longer evaluated during only scheduled inspections. They are progressively becoming machines that report their own structural condition. At the same time, aerodynamics determines whether the aircraft fulfills its economic mission. While wind tunnel validation remains indispensable, computational fluid dynamics now performs much of the early aerodynamic refinement. This enables engineers to simulate airflow across millions of data points and adjust surfaces with remarkable precision. Minor contour modifications can translate into measurable fuel savings when compounded across decades of operation. Research into laminar flow continues throughout the industry, although maintaining it consistently in airline service remains technically challenging due to surface contamination. Even engine nacelles and nose shaping are refined through these simulations to minimize drag. Passengers will likely never notice these aerodynamic subtleties, but airlines absolutely will, because efficiency scales with every flight hour. Regulatory scrutiny has intensified across the aerospace sector and ensures that any new aircraft must demonstrate compliance across thousands of safety criteria under worst-case conditions, including engine failure during takeoff, rejected departures at maximum weight, crosswind controllability, emergency evacuation timing. Nothing is assumed, and everything is demonstrated. Certification alone can consume close to a decade when development and testing are combined. This explains Boeing's repeated emphasis that its next aircraft must be launched only when technological readiness, along with supply chain stability and regulatory pathways, align. Until that moment arrives, the 797 remains what it has long been, a serious engineering study, refined but not yet approved. And history suggests that some of aviation's most influential aircraft begin exactly this way. About that question from earlier, Specialized aircraft offer optimized efficiency and payload capability on routes that are beyond the practical limits of single-aisle jets. However, increasingly capable narrowbodies provide lower operating risk, greater scheduling flexibility, and easier airport compatibility, which makes them attractive for airlines prioritizing frequency and cost control over maximum capacity. The NMA is not a promise yet, but the technologies expected to shape it are already influencing how future aircraft will be engineered, manufactured, and certified. If launched, it would likely mark one of Boeing's most consequential design decisions in decades. For years, the largest version of Boeing's next widebody family felt like a ghost aircraft. Talked about quietly, studied internally, then shelved while more urgent problems took over. But suddenly, a single announcement at the Dubai Air Show changed the tone of the conversation. The 777-10 is not a clean sheet aircraft. It's a stretch of the already enormous 777-9, which is the largest member of the 777X family. Boeing has studied this idea since the early 2010s, when engineers confirmed that stretching the airframe was technically feasible. The problem was never whether it could be done. The problem was whether it should be done. For most of the last decade, Boeing focused on certifying the 777-8, the 777-9, as well as the freighter variant, all of which remain delayed. With those programs consuming resources and attention, the stretch quietly went dormant. That changed when the airline's Emirates publicly backed a feasibility study. Their order for additional 777-9s came with something far more important than money. It came with intent. Emirates made it clear they are willing to anchor the program if Boeing decides to move forward. And that statement is a major reason as to why the 777-10 is being discussed seriously again. The proposed stretch is substantial. Boeing studies suggest an increase of roughly 16 feet over the 777-9, which would push the total length close to 268 feet. That would make it longer than a football field and also the longest passenger aircraft ever proposed. Cabin capacity estimates hover around 470 passengers in typical high-density layouts, but there's still room to go higher depending on configuration. This matters because the aircraft would sit in a unique space. It would approach the capacity once dominated by the Airbus A380, but with 2 engines instead of 4. That alone drives almost every design decision Boeing would need to make, such as takeoff performance or structural reinforcement and certification margins. This creates a question. Does the data and gap from the A380 actually support building an aircraft this large in today's market, or is this a case of an ambitious airline pushing risky development instead of economics? Let us know your thoughts in the comments below, and we will discuss this later in the video. At first glance, stretching a jet looks like a fuselage problem. Add plugs, reinforce frames, extend systems. But for the 777-10, the real starting point is the wing. The composite wing developed for the 777X was already designed with growth in mind. Its folding wingtips allow a massive span on the ground without exceeding airport gate limits. That same wing provides the lift margin Boeing would rely on to carry a heavier and longer airframe. That same wing already carries higher bending loads than previous 777s, with its longer span and higher aspect ratio. Boeing's study focuses on whether that margin is sufficient for the added fuselage length or if localized reinforcement at the wing root and center wing box would be required. However, any reinforcement would increase structural weight, which then feeds back into fuel burn, range, and ultimately also takeoff performance. Essentially, Boeing is testing how far the existing wing can be pushed before those trade-offs outweigh the capacity gains. The 777-10 would almost certainly use a derivative of the GE9X, already developed for the 777-9. But the 10 would push further and leverage the GE9X's efficiency and record-setting thrust of around 110,000 pounds for greater passenger numbers. So far, the aircraft remains under a Boeing feasibility study, driven by interest from airlines such as Emirates. But its thrust is not the limiting factor since the GE9X produces more than enough power. The challenge actually lies in certification scenarios and particularly engine-out performance during takeoff. Regulations require a twin-engine aircraft to safely continue takeoff after the failure of one engine at the most critical point. For an aircraft of this size, those margins become extremely tight. Boeing has made it clear that this is one of the biggest technical hurdles. Can the aircraft maintain directional control? Can it climb at the required gradient? And can it do so within runway length limits at major airports? And all these questions are not theory. In fact, they play a major role in determining whether the aircraft is certifiable at all. The 777X's longer fuselage raises tail strike risk, so Boeing added software-based protection into the flight control system. During takeoff, the aircraft limits pitch rates to keep the tail safely clear of the runway. However, this is not viewed as the primary challenge for a potential 777-10 stretch. The dominant concern remains certification-level takeoff performance, especially engine-out climb requirements and runway limitations, which become increasingly restrictive as aircraft size and weight grow. If the 777-10 requires longer runways or lower payloads or reduced range at busy airports, its market shrinks instantly. Boeing's feasibility work focuses on modeling these scenarios across real-world airports. This includes cities and airports like Dubai, London Heathrow, Los Angeles, and other slot-constrained hubs where aircraft of this size actually make sense. Stretching an aircraft always adds structural weight. Frames get stronger, landing gear loads increase. Boeing knows this already, but what they're trying to estimate is by how much the weight will actually increase. Every added ton must be justified by revenue potential. If the aircraft carries more passengers but sacrifices too much range or cargo capacity, airlines lose flexibility. Boeing's internal modeling weighs seat count against payload range curves and looks for a balance that keeps the aircraft economically viable across multiple mission profiles. Emirates is still pushing for the development of the 777-10. For them, the aircraft seems to be a strategic necessity more than a flagship. As the world's largest A380 operator, they built their entire network around high-capacity aircraft, feeding a global hub. What that means is Emirates cannot simply add more flights as demand grows. Their only scalable option is to move more passengers per departure. But that model only works if similar capacity exists in the future. The A380 fleet will not last forever. Production has ended and any new variant will not be coming. As the A380 fleet ages and production remains closed, support costs will rise and capacity will inevitably decline. No current twin-engine aircraft fully replaces what the A380 provides. A stretch 777 comes closest and combines high capacity with lower operating costs. Without an aircraft like the 777-10, Emirates would eventually be forced to rethink its hub strategy and accept structural limits on future growth. Boeing's caution comes from simple math. The global replacement market for aircraft seating over 350 passengers is estimated at around 1,000 aircrafts, keeping in mind various market industry analyses. That includes aging A380s and older 777-300ERs. This means it is not a high-volume market by any margin. Launching a new variant requires confidence that development costs can be recovered, and Boeing is not in a position to gamble lightly. They have to weigh every single decision against certification delays, as well as production constraints and ongoing recovery from past crises. The timing of this study also matters. Airbus emerged from the Dubai Air Show with major wins across widebody and narrow-body segments. Airlines that once relied almost exclusively on Boeing are diversifying. That shift adds pressure. At the same time, Boeing's 777X program remains uncertified and is now years behind schedule. The Federal Aviation Administration's oversight environment is stricter than ever. Any new derivative would face intense scrutiny from day one. Now the 777-10 cannot be rushed, and Boeing knows it. If approved, the 777-10 would follow the same production architecture as the 777X. Major fuselage sections would be manufactured globally and assembled at Boeing's Everett facility. Composite wings would continue to be built in Washington State. Systems commonality with the 777-9 would be maximized to reduce complexity. What will change is scale. Longer fuselage sections require new tooling adjustments, and assembly flow would need recalibration. Even ground handling procedures would be updated, and factors like hangar compatibility also become a consideration at this size. Ultimately, the 777-10 lives or dies on certification margins. Boeing can solve engineering challenges, but the harder question is whether regulators are satisfied with safety margins under worst-case conditions. That includes rejected takeoffs as well as engine failures and abnormal configurations. And until those questions are answered through analysis and testing, the aircraft remains a study, not a launch, not a promise. just a possibility grounded in data. And that question from earlier? Data supports development of this aircraft only in limited conditions. Factors like slot-constrained hubs and rising long-haul demand with Emirates' hub-focused model justify it. But the global market remains narrow, which means profitability would depend on a small group of high-density operators rather than widespread airline adoption. But 777-10 is not about breaking records. It is about whether the industry still needs ultra-high-capacity aircraft in a twin-engine world. Boeing is studying that question carefully, and for the first time in years, the answer is no longer obvious. If you want more deep dives into how aircraft are actually designed and certified, like the video, subscribe, and share your thoughts below. And let us know, do you think the world needs a 777-10?